There are two types of substitution reaction: nucleophilic substitution reaction and electrophilic substitution reaction. In a nucleophilic substitution reaction, the substituent is a nucleophile, and in case of an electrophilic substitution reaction, the substituent is an electrophile. Now, in English, phile means love or attraction. So, a nucleophile is that which has a love or attraction towards nucleus or a positive center. So, a nucleophile must have a negative charge or lone pair electrons, and an electrophile has attraction towards electron or negative center. So, an electrophile must carry a positive charge. In nucleophilic substitution reaction, there are also two types: unimolecular and bimolecular. In unimolecular, it's a two-stage process. The first stage consisting of slow heterolysis of the compound to form a carbonium ion, followed by rapid combination between the carbonium ion and the substituting nucleophilic reagent. Since the rate determining step is the first one, and since in this step only one molecule is undergoing a covalency change, this type of mechanism is called unimolecular and is labeled Sn1. In case of a bimolecular reaction, this is a one stage process. Two molecules simultaneously undergoing covalency change in the rate determining step. This type of mechanism is called bimolecular and is labeled Sn2, since the rate determining step in this reaction is the formation at the transition state, the hydrolysis of an alkyl halide by Sn2 reaction is given by substitution. S for substitution, N for nucleophilic, and 2 for bimolecular. A number of differences exist between Sn2 and Sn1 reaction. When both reactants are present in small and controllable concentrations, Sn2 reactions are second order and Sn1 reactions are first order. The Sn2 mechanism always leads to inversion of the product, whereas with the Sn1 mechanism, the configuration of the product depends on various factors. No rearrangement is possible for the Sn2 mechanism, but is possible for Sn1. The rate constant of an Sn2 reaction with a given substrate depends on the nature of the nucleophile, and for a given nucleophile on the nature of the leaving group of the substrate. Now, Sn1 reaction passes through the formation of a carbocation, and the carbocation is formed in the rate determining step. So the stability of the carbocation that depends the overall rate of the reaction. More the stable carbocation formed, more or faster will be the rate of the Sn1 reaction. Again, the stability of the carbocation depends upon the presence of methyl substituents. Methyl group has plus a inductive effect, so having a greater number of methyl groups in the carbocation, more stable will the carbocation be. And again, methyl group has the hydrogen atoms which are hyperconjugable hydrogen atoms, and hyperconjugation is predominating over the methyl over the inductive effect. So the more the methyl substituent present in the carbocation, more stable the carbocation will be. Sn2 reaction passes through a transition state. In the transition state, the incoming group and the leaving group are collinear and on opposite sides of the attacked carbon atom. Furthermore, the line joining the entering group and leaving group is perpendicular to the plane containing the other three groups. In the original molecule, the four groups are arranged tetrahedrally. Hence, to achieve a planar configuration, in the transition state, the carbon atom changes from tetrahedral to trigonal hybridization, the remaining orbital being used to hold the groups, the leaving groups, and the entering groups by half bonds. When leaving group is ejected, the carbon atom returns to the state of tetrahedral hybridization. Now we can see the rate of the reaction increases for Sn1 increases from tertiary butyl chloride to methyl chloride. The steric effect, originally thought to be a special effect brought into play by mechanical interference between groups and was described as steric hindrance. The term steric hindrance considered the geometry of the reactant molecule. When, however, a molecule undergoes chemical reaction, it does so via a transition state. In case of Sn2 reaction, in case of Sn1 reaction, steric hindrance is not a factor, but the factor is the presence of methyl substituent as the Sn1 reaction passes through a formation of a carbocation. So tertiary butyl chloride has that carbocation formed after elimination of chlorine or rejection of chlorine. The carbocation has three methyl substituent which are showing their plaza inductive effect as well as hyperconjugation. So tertiary butyl chloride, the carbocation formed from tertiary butyl chloride will be more stable, and methyl chloride, which forms a 1 degree carbocation, will be less stable. That is why the Sn1 reaction increases from methyl chloride. The rate of Sn1 reaction increases from methyl chloride to tertiary butyl chloride, whereas the Sn2 reaction rate decreases from methyl chloride to tertiary butyl chloride as the more and more bulky methyl groups are present in the transition state. Steric hindrance will be more, and that will destabilize the transition state, so the rate of the reaction will also be decreased. Now let us consider the stereochemistry of Sn1 and Sn2 reaction mechanism. In an Sn1 reaction, a carbocation is first formed in the rate determining step, and then the incoming group or the substituent, the nucleophilic substituent, comes. Now since the both sides are open, the nucleophile can attack the carbocation from either sides, so there is a possibility to form both of the isomers, of course optically isomers, in 1:1 ratio, because probability is equal to form the two enantiomers. Now for the presence of two enantiomers in 1:1 ratio, the solution becomes optically active. An optical activity of a compound is its ability to rotate the plane of the polarized light either in clockwise direction or in anti-clockwise direction. If it does it in clockwise direction, then it is called dextrorotatory, and if it does it in anti-clockwise direction, then it is called levorotatory. Now if two enantiomers are present, both dextrorotatory and levorotatory are present, then one will try to rotate the plane of the polarized light in right hand direction, or the other will try to rotate it in the left hand side or in anti-clockwise direction. So ultimately the solution will not be able to rotate the plane of the polarized light when pass through that solution in either direction. That's why the solution becomes optically inactive, and this mixture of 1:1 ratio of two enantiomers is called racemic mixture, and that incident is called racemization. So in Sn1 reaction, racemization occurs, wherein in Sn2 reaction, since one side is blocked, in the rate determining step, the entering group has to come from the back side of the leaving group. Therefore here always inversion of configuration occurs.